Thank you for being here, either in person or online, at our McGill Friday noon seminar. Today, we have the pleasure of welcoming Dr. Heather Whitney. She is a research assistant professor in the Department of Radiology at the University of Chicago. She did her grad school, her MSc and Ph.D. at Vanderbilt University. And she is conducting research in computer-aided diagnosis of breast and ovarian cancer, among other things. So I will let her explain to us what she's been working on. Please take it away.
Hi, thanks so much. And I'm so honored to be speaking to you all at McGill today. I have such a high opinion of your department and the great things you're doing. And I've interacted with the McMed Hacks competition a couple times, as well as a judge and as a speaker. So you all are doing just great work there, and I'm excited to share with you some things that I'm doing. And so first I'll introduce some of the things, get my background. And I'm giving my background because I think it influences my work today, of course, and I want to share a little bit about that. So as Peter mentioned, my graduate training was at Vanderbilt. So I have a master's degree in medical physics as well as a PhD in physics. And I trained at the Institute of Imaging Science there. So if you don't know the VUIIS at Vanderbilt, definitely a place to check out the good work they're doing. And I worked with George Ding as my master's advisor and John Gore as my PhD advisor. And they were very influential to the work I do today. So I like to mention them. And in fact, my graduate work focused on polymer gel dosimeters. And so if you know kind of what that means, but I wanted to show just a few images. So this is a system where we take radio sensitive materials such as polymers and put them in a gelatin matrix and irradiate them. And it brings up all kinds of interesting studies, especially for magnetic resonance relaxometry, optical studies, and also for 3D dimensional dose distribution measurements. So we like to irradiate things in the Vanderbilt V, as you see here, which seems a little, self-promotion for Vanderbilt, but actually it helped us study some really tight margins on radiation dose distribution. So it was a great study there. And then previously, I was actually, before coming on full-time at the University of Chicago, I was a visiting scholar in radiology for several years, while also a faculty member at a small liberal arts college. And while there, got an NIH R15 grant to do breast cancer radiomic studies. And then actually came on full-time to the University of Chicago about a year ago as a research assistant professor. And so my experience is really all across the imaging chain, from phantom development to image acquisition, to quantitative analysis, curve fitting kinds of things, and then on to artificial intelligence. So as I speak to you, I really think of myself as a physicist through and through that uses a number of different techniques for studying medical images and how we use it in practice. And I'm also really, really interested in the decision-making derived from medical images. So actually, right now, I'm in a fellowship at the McLean Center at the University of Chicago for clinical medical ethics. And it's really providing me great insight into how do clinicians think about their decisions. And also, we're forming some interesting work on how principles from artificial intelligence and medical imaging, how do we apply that in an ethical way, but also how might we use what we know from medical imaging to maybe resolve some ethics conundrums that arrive in medicine. So it's proving to be very interesting. And I want to give you a broad overview of the current projects I'm doing. So I do a lot of work in breast cancer, computer-aided diagnosis, and AI, working in the modalities of dynamic contrast enhanced MRI and digital mammography. I work a lot in lesion-based repeatability, which will be a focus that I'll talk about today. Also in data harmonization, health disparities questions, and multimodality and multiparametric work. And also, as I mentioned, ethics and clinical decision-making based upon medical images. I'm also working in projects in adnexal cancer with the ultrasound modality. So here are some of our recent results with doing some segmentation work. And then I also work in COVID-19 imaging with chest radiography and CT imaging. And we're doing a number of different initiatives, and I'll talk about those during the end of my talk. So I also just want to make sure everybody has kind of a good conception of what we're trying to do in AI. I know a lot of people in your department do deep learning of AI, and as you know, it's amazing technology there. And I work in that. I also work in human engineered AI, and I think it speaks to me a lot because of my nature as a physicist. I love kind of the hands-on measurement work, as in addition to the capabilities that deep learning gives you. But as we work on human engineered AI of breast cancer on MRI in particular, we think of this as being able to analyze a virtual biopsy of the tumor. And so a lot of our work is driven towards those goals. So we do automatic segmentation analysis and in 3 dimensions. As you know, these methods are non-invasive, which has benefits to the patient, covers the complete tumor, and that helps complement the work in biopsies because biopsies can miss some tissue. So we're interested in what can an MRI image get you as a total view of the tumor, and then it's also repeatable. So we conduct some methods such as segmentation using fuzzy C-means. We do feature extraction, merging classifiers, and measuring malignancy or aggressiveness. Many of you are familiar with these topics, but if you're working only in deep learning, I wanted to make sure you had an idea of what happens at the human engineering level as well. And we're extracting features such as size, shape, morphology, and features related to contrast enhancement for DCE MRI. And I also want to make sure we kind of place what I'm about to talk about in terms of the overall clinical workflow. So let's say a patient gets imaged, and this is the ideal. This is where we hope to end up with our AI models. Let's say the images are evaluated using some kind of model that's gone through total FDA approval in the clinic, workable, validated, all those good things. And let's say, again, the ideal is that a report would provide the AI model's prediction for the patient's status in some way. And then what we're all going for here is that a clinician sits down with that information and uses it for that patient as one piece of their decision making. They've also got lab results, they've got their own observations. The AI information is one piece of the final decision from the physician. And behind the scenes, we have for these FDA models, rigorous development and validation. There's data from many patients coming in to contribute to the performance of evaluation that led to the FDA approval. But there are some important questions for this clinical translation, and that's going to be the focus of my talk today. Some questions I'm interested in are, how sure is the model about the prediction for an individual patient? And this is important when we give that information to the physician. We don't just want to give them a likelihood, but they need to have some kind of margin on there. And so I'm working on methods for that kind of methodology. We also want to understand, how do differences in reference standards impact performance? So when a patient is given a diagnosis, let's say in breast cancer, as I'll talk about, molecular subtyping happens, and that's, a conclusion is made about what is the molecular subtype. That can impact what kinds of treatment decisions are made. If we want our AI models from imaging to complement those or contribute, but there's differences in those reference standards, we want to understand how might that impact the performance evaluation. And then finally, if we've got data ideally coming from many, many patients, how do we ensure that our models are developed from high quality and representative data? All of these things are kind of patient level questions, even though they're in the big picture of AI and medical imaging. So here's an overview of what I'm going to talk about. We've had 2 recent papers come out that I'm going to discuss. One is on sureness, which is a metric we're proposing for patient level classification, repeatability. And we're using it in the use case of breast cancer diagnosis. Can be used in others as well. We want to understand the impact of reference standards differences on prediction of molecular subtyping from DCE MRI. And then I'm going to talk about the need for data in AI development and share with you a lot about MIDRIC, which is the Medical Imaging Data and Resource Center in which I'm an investigator. So first, I'll share about sureness. So again, if we go back to this idea of physicians sitting down with the information from an AI model, assuming the whole pipeline is all set up, there are a couple of pieces of information that they might be getting. So one is they might be getting a measurement that there's a low likelihood of a diagnosis of cancer. So the question is, on an image, is the lesion cancerous or not? Maybe it's a low likelihood, a high likelihood. But as you can think about it, maybe there's a sense of sureness behind that model. So is the model very sure about that prediction? You can be very sure that it's not cancer, or not very sure that it's not cancer. So if you think about these combination of factors, we can have kind of 4 different domains that are really, I think, important to share with a clinician. So for example, at the top left, maybe there's a low likelihood of a particular patient outcome, and there's a high sureness of that likelihood. But if you think at the bottom left, there may be a low likelihood of a particular patient outcome, but maybe in terms of the assessment, the model's actually not very sure about that. That would be really important to give nuance to the physician about for their decision making. And then likewise, we have the complementary versions of a high likelihood, high sureness, or low sureness. And so what we're interested in is especially these territories where you might be giving some kind of output from the AI model, but the model's not very sure about it. And so the motivation for our work is that if you think about all the papers you've seen, all the work you've done on assessing AI models, we use the AUC, the area under the ROC curve, as a figure of merit for measuring classification performance. Great metrics, so interesting to work with, but it uses all the data. And so AUC informs AI developers about that performance across the whole entire decision threshold and reflects all the cases. Again, really interesting. But if we go back to the classifier output distributions and we study them under, in the situation I'm working with, variation in training, we can characterize the repeatability in AI prediction for a single patient. And I want to emphasize this is not repeatability of radiomic features, for example. That's really interesting work that's very important. But that's not kind of how repeatable is a feature measurement. We're talking about how repeatable is a prediction for a single patient. And so I want to share with you the pipeline that we developed to study this in the use case of breast cancer diagnosis from DCE MR images. We're taking the 4D images and we conduct automatic fuzzy C-mean segmentation. We're using 32 computer extracted human engineered radiomic features. These have been used in the Geiger lab that I work in for a long time, and they've been well validated for these diagnosis questions. And then we use a bootstrapping method called the 632 bootstrap method, which allows you to place cases in training and testing and control for a bias correction that needs to happen. And you can vary what goes into training and testing. And so in each one of those bootstrap folds, we conduct feature selection if applicable. That's, for example, if you were doing a linear discriminant analysis classifier, you might do feature selection first. Or if you're doing an SVM classifier, we've done both of those in this study, you wouldn't do feature selection. But in the end, you do classifier training of the classifier lesions, and then you get a likelihood of malignancy of all the test lesions. And then you can use that to evaluate classification performance, just like you would in kind of a typical study. But you can also use that likelihood of malignancy for each lesion as the training underwent variability, and then get what we are calling repeatability profiles. And I'll show you an example of that. And then you can assess that impact of variability for a single case by evaluating sureness. And when we developed the sureness metric, we wanted to take something simple and intuitive. Again, with that clinical decision making, a physician sits down with it and is making a decision with it. We wanted it to be as simple as intuitive as possible. So we defined sureness as 1 minus the 95% confidence interval of likelihood of malignancy. That is assuming that your classifier output is scaled from 0 to 1, but this is what we're working with here. And so first I want to show you a repeatability profile because it builds into then what we look at a lesion base. So this figure shows on the x-axis the likelihood of malignancy, and then on the y-axis is sureness. So higher is better in terms of sureness. And then each dot here is a case in our study. And we do have a lot more cancers than benign lesions here. So you're not just imagining that. That is actually the imbalance behind the scenes, but we've controlled for it. And so what we look at here too is we've binned these with some histograms that help kind of see the pattern behind the scenes. But what I'm going to focus on is the fact that each dot represents a combination of median likelihood of malignancy and then sureness. And so we find some really interesting behaviors and things behind the scenes. So for example, here we see some cancers that actually have, they're biopsy-proven cancers. They have a low likelihood of malignancy from the model. And the model is very sure about that, which is very interesting. We also have benign lesions that have a high likelihood of malignancy, and the model is very sure about that. Then we have two other combinations. We have lesions with a low likelihood of malignancy. It almost, checks the box mentally, benign lesion, low likelihood. However, the model is not very sure about that. And then we have cancers with a high likelihood of malignancy, high median likelihood of malignancy, but very low sureness. Again, the answer you think matches with the actual state of the lesion, but the model's not very sure. And we also have some combinations where we have lesions with a similar likelihood of malignancy, but very different sureness. So if we look at these, there's a green dot here and dot here, about 20% likelihood of malignancy. Again, looks similar at face value, but very different sureness. And then similarly for two example cancer lesions. So what we have done is we produced a method that not only gives for that single patient output, which is really at the end of the day what the physicians are interested in. We've given a measure of how sure it is, and we hope that it's intuitive. And so our next step is to run some reader studies where physicians sit down and we study what they do with this information. It also really helps with pipeline development in some interesting and innovative ways. So we were interested in this study asking the question, if you're sitting down and you're trying to think about pipeline development and you're trying to decide between classifiers, how do you make that decision? And this study ended up being really interesting because if we take our task to classify these lesions as malignant or benign, and your question is, evaluating if one classifier may be preferred over another, which is actually a really difficult thing. The literature points to how difficult this question is. We find that if you compare the AUCs, there's no statistical evidence for performance between the two classifiers in terms of AUC. So what we have here is the AUC curve. We use linear discriminant analysis and SVM classifiers. We show the AUC here. We're looking at the difference in AUC. These are from bootstraps. And because this confidence interval crosses 0, there's no evidence for difference. So you might pause and say, well, it doesn't matter which one you choose. But if you look at this from a sureness perspective, you start to see some advantages for one versus the other. So here again, our sureness cases as described. And so on this figure on the left, I'll walk you through it. We have on the x-axis, first I'll point out, we have the little dots are the individual cases, individual lesions. The x-axis is the difference in sureness from when you use for each lesion the LDA classifier or the SVM. And then the y-axis is the difference in percent of bootstrap folds with correct classification. So we did choose an operating point here. We chose a target 95% sensitivity operating point, and then said at that operating point is one classifier resulting for a correct classification or not between these two classifiers. And we identified kind of 3 tiers of lesions. So if you look at the bottom left, this is tier 1 in terms of the SVM, kind of the best case scenario, where these lesions that would appear down here, kind of they're in this quadrant, better sureness when using the SVM and more frequently classified when using the SVM. Then we have tier 2. These are the ones that are along this 0 line here, but they have better sureness with SVM. So that's kind of why they're aligned in this area here. And then equal frequency of classification. So while you might not get a gain in terms of frequency of classification, you have improved the sureness for those lesions by using the SVM. And then we have kind of the opposite. We have better sureness with the SVM, but actually LDA, very interestingly, more correctly classified lesions. So we have these different tiers, and then the tiers go in reverse when you're thinking about the LDA. And then we also have this for the malignant lesions. So I'm going to highlight this section here and then show you briefly the scatter of figures here for the malignant lesions, kind of similar tier setup. And if we kind of pay attention to these sections here, I want to summarize these. Overall, we concluded that there was evidence for better sureness and at equal frequency of correct classification when using SVM. So if we first look at AUC, no real evidence for choosing one or the other. But if you choose the SVM classifier, you get gains in sureness while maintaining classification accuracy, kind of frequency of getting that correct. And here's a quote from our paper. So using the SVM classifier would result in a net gain of sureness for 16% of the benign lesions. 33 benign lesions would have an improvement of sureness. And 307 malignant lesions would have an improvement in sureness while maintaining that lesion-based performance. So this does give evidence for which classifier to prefer. And so we recently published these results in Medical Physics. I'm really excited that 3 of my former students, undergraduate students, are co-authors here, Michael, Amy, and Michelle, as well as my wonderful collaborators at the University of Chicago. And so in summary, we found that the sureness metric can measure how sure an AI algorithm is of its prediction for an individual patient. And it can also work as an additional tool for pipeline evaluation. We have some really exciting work we're going to do in using those kind of, off-kilter results when you have a high probability of malignancy, but low sureness. All those different combinations are going to allow us to dive in at a patient level and try to understand those lesions more in terms of the AI models and how they work with them. So now I want to talk about impact of reference standard on prediction of molecular subtype from DCE MRI. Really interested not only, calling lesions malignant or benign, but getting more at their nuances, and especially, as I mentioned, kind of interoperating with how a biopsy is a really important tool in cancer diagnosis, but biopsies, grab a certain section of tissue, and then can imaging come alongside that and give kind of this comprehensive 3D view of what's in the lesion in terms of maybe predicting what types of treatments are important. So if we think along the whole AI medical imaging pipeline, we conduct data collection, we prepare and annotate the data, we develop models and evaluate them and deploy them. We think about the whole chain here. But what I want to focus on is this question of data preparation and annotation. So if you are working in supervised learning, those labels have got to be good. And so much can happen there. And that's the focus of what I'm discussing here. So if we take the substantial interest in extending AI and computer-aided diagnosis to identify the molecular subtype of a breast lesion using medical imaging, it's an interesting area. There are some differences in at least two common reference standards for determining molecular subtype. So molecular subtypes are often described as, luminal types, luminal A, luminal B. There's basal cell, there's normal-like, and I'm focusing here on the luminal types. And so if you look at luminal A, luminal B, often once that designation comes in, a physician will then plan treatment based upon that. And they have other information, of course, but I'm focusing on molecular subtype here. And two common reference standards are used to determine those. One is immunohistochemical, IHC. It uses different receptor types informations. And then there's the St. Gallen criteria, which uses Ki-67 in addition to these. And so what institution uses which molecular subtype can depend upon a number of different factors. It actually can relate to resourcing as well. So, low resource institutions might use the IHC version versus St. Gallen. And this difference came up in an international collaboration that we were doing with some investigators in China, where we sat down to work on molecular subtype questions and realized actually if you subtype these by one criteria and then another, you have a set of lesions that actually is one or the other based upon which criteria you're using. So that was a really kind of clinical driven question here that we were interested in. And so I'm going to show you an example of 3 different images. So these are DCE MRI images. These are the second post-contrast images for 3 patients. And the one on the left is luminal A by both reference standards. The one in the center is luminal B by both reference standards. But as you might guess, this one's interesting. The IHC classification system would call this luminal A, and the St. Gallen would call this luminal B. Very interesting to think about. And so we were curious about how does this impact, classification performance? And then also, can imaging help separate these into some different kind of systems for subtyping? That's kind of our bigger question that we have. But I'm going to talk about classification performance. In this database, we had 877 unique cancer lesions that were either luminal A or luminal B, kind of no reference standard that we work with, put them in any other category. And these were imaged at 3T using GE scanners. We conducted lesion segmentation and feature extraction. We did the molecular subtype determination, and we ended up with 3 groups of lesions. Luminal A agreement lesions, both systems call those luminal A, luminal B agreement lesions, and then the disagreement lesions. And we were interested in assessing that impact on classification performance and the task of, from imaging, predicting molecular subtype. So I wanted to emphasize too here, where are the differences between the systems? So here are 2 references. If you want to jot them down and start exploring this yourself, you can look at Tamimi or Goldhirsch for these. And the real key difference is the introduction of the Ki-67 biomarker. It's a measure of cellular proliferation. And so the St. Gallen standard says that if that's below 14%, call it, and has all the other criteria here, call it a luminal A, call it a luminal B if it's above that, whereas the IHC is not taking in that information. So the difference in classification for the disagreement lesions can really come from, do you have Ki-67 available to you or not? So here, I wanted to show visually our kind of allocation of lesions. So these 3 combination of lesions, as you see here, we take all the lesions and think about kind of 3 different groupings. So if you use just IHC, you have, a large number being luminal A and a smaller number being luminal B. If you use the St. Gallen, most of them are actually luminal B. and luminal A. And then you can think about a grouping where what are the lesions that are just in agreement by both categories here. So I wonder, we might have another mouse in play. Peter, I don't know if you can check into that, but I'm not moving the mouse actually right now. So, and just a heads up for anybody else who might see anything advancing, we might have another mouse in play. So we were interested in using cross-validation, and we use stepwise feature selection followed by linear discriminant analysis here in these different groupings. So you can see the number of lesions that appear in the classification performance differs by which kind of grouping you have. And so for each molecular subtype determination, we classify those lesions using the Wilcoxon method within the cross-validation. And a statistical rigor is really important in our work. So we tend to stay away from kind of assumptions about normality. So we're using the empirical median and 95% confidence interval of the area under the curve using a posteriori bootstrapping. And we did 3 pairwise quantitative comparisons where we were comparing the classification performance between the 3 different groups. Just note here, these are kind of different numbers of lesions between all of these, so we did not have to do any corrections for multiple comparisons. And our criteria for significance was p less than 0.05. And so what we found here, here's the ROC results. So on the left, I have the ROC curve. The broad dashes are for the AUC here for using IHC. We have the St. Gallen criteria. Again, I'm not moving the mouse, so I'm not sure what's up, but it does seem to be following my speaking quite well. So we'll just note that. And then the solid line is the agreement in molecular subtype. What happens when you have classification performance in that form? And so here are the differences in AUCs, and we're looking at what is significant. And I'll highlight to you that the classification performance was statistically significantly superior when using only agreement lesions. When you introduce these kind of disagreement lesions, it actually kind of befuddles the classification performance and drops it, which we found to be very interesting. So we've published these results in Radiology earlier this year. We're very excited about that. And so in summary, disagreement in this determination of breast cancer lesions as luminal A or luminal B due to differences in reference standards, these can impact the characterization of imaging phenotypes for these molecular subtypes and reduce classification performance. It's really interesting when you read the literature and look at other studies that have done questions in classification performance by molecular subtype. They're often using one or the other, and that can become important for generalizability of their methods. Also, we think that these findings suggest that using imaging phenotypes of breast lesions could potentially help advance the characterization of these lesions. It's almost like working in reverse. If we can take some studies of these disagreement lesions and kind of compare how they compare to, consensus agreement luminal A's and consensus agreement luminal B's, or are they a different subtype altogether? This could complement molecular subtyping work. In fact, the paper also addressed this, and I have some additional slides that I can talk about when we get to the discussion time if you're interested in, because we were also interested in how did the imaging phenotypes tell us about this disagreement category. So now I want to talk about the need for data in AI development, role of MIDRC. And I do a lot of work as an investigator in MIDRC and wanted to share with you all about that. So first, it's important to use the pandemic and all the imaging hopes and dreams that came out of that as a pause moment to think about, we had this situation where massive AI models could be helpful, and a lot of people were working on this. And as we sit back and reflect on that kind of burst of activity, some major concerns come out. There's been some, think pieces that have discussed about how hundreds of AI tools came out. The conclusion could be that none of them really kind of impacted in a substantial way. And some things that come out when we reflect upon the pandemic and AI of medical imaging are poor quality of COVID imaging data. So as we constructed these massive data sets, some of the data was mislabeled. A lot of it had multiple unknown sources, duplicate data. So sometimes training and testing allocations were not clear cut, no traceability, and lack of external validation. Some other areas that when we reflect that are of concern is, lack of collaboration between AI experts and biomedical experts. So something that I think is just really important is if you're working on algorithms to be in discussion with clinicians. And so sometimes papers were coming out where they were solely focused on the code base and performance, technically by algorithms, but we needed to have some closer collaboration with biomedical experts. And so that emphasizes the need for valid ground truth. How do you even define ground truth? So important. And the need for a totally independent test set. Super important. And then we also saw some issues with bias, diversity, and representativeness of data. So often data was collected for a specific clinic. Often we saw kind of, really narrow profiles of the patients coming to those clinics. But if you try to transfer those models elsewhere, didn't work so well. And sometimes, single experts were scoring these things, and there wasn't enough time necessarily to bring in multiple experts, given the pace that everybody needed to take for these models. So one of the answers for AI development and improving it is lots and lots of data. And that's a really worthwhile effort to make. It's been noted that approximately 80% of the development of AI corresponds to the data collection and data preparation steps. Those are like the first two things along the pipeline. And so if you think about those 5 points along the pipeline, almost weighting the size of those boxes according to kind of the time and effort needed for a good deployment at the end, those boxes would be huge at the very beginning. So no doubt we need lots of data for AI development. But that doesn't actually solve all the problems that were previously listed, especially with COVID imaging. So you can actually kind of shift this phrase a little bit to not only do we need data, but we have specific needs of data in the development. And I'm going to emphasize here that the data needs to be high quality and representative. And I want to give you some practical insights into how MIDRC specifically seeks to address these issues to accelerate the deployment of AI and medical imaging in medicine. So today, right now, I'm speaking as an investigator within MIDRC. So if you haven't heard about it, it's the Medical Imaging and Data Resource Center. And you can get there by going to midric.org or data.midric.org. Hopefully pretty easy to remember or jot down if you'd like to put it in a tab and look at it later on. And I want to introduce to you kind of just what it's about and how big is it and what are we doing. So this was established in August 2020 as a kind of a rapid response to the COVID pandemic and accelerating the ability to develop AI tools. But COVID is kind of the first use case. So it was launched kind of in those emergency situations, but actually it's bigger than COVID, and our footprint is growing to reflect that. So what's I think really interesting about MIDRC is it has, it's based at the University of Chicago, but it has really, really close collaboration and involvement with 3 professional societies, AAPM, ACR, and RSNA. All of them are really contributors to the actual pipelines we're setting up and the evaluation procedures we're doing. And then the data is hosted at Gen 3, which is a data commons. Also, they work with genomics data and all kinds of different types, and they are wonderful partners in our work. So in short, right now, MIDRC is an image, you might think of it as an imaging data commons. Certainly we hold data, and we'll talk about that. And it holds a lot of COVID imaging data, but more broadly, it's an open, curated, and diverse set of data. So we not only have data, but we actually have 2 scientific components. There's the data commons, and it has almost 160,000 imaging studies have been released to the public. This represents over 67,000 unique patients. And it's ready to go for AI investigators. You can start up an account today and start downloading data, which is really neat. And then we also have computational capabilities that we're developing. So we develop tools for accelerating AI and medical imaging research. So for example, we work a lot with making a decision tree for metrology. What are the best kind of ways to evaluate these algorithms? How do we assess diversity and bias in the data? We have a sequestered data set, which I'll talk about. That is specifically meant to translate our people's work through regulatory mechanisms. And we also have resources such as a YouTube channel. So right now, there's over 100 investigators from a number of different stakeholder type groups that work within MIDRC. And all of that data is aimed to be AI-ready imaging-free studies that are free to researchers. So I want to talk with you too about kind of the method of collecting data, because I'm emphasizing high quality nature of the data right now and how important this is for AI imaging. So we start with images that come in from data contributors at different medical centers. And these come in to one of 2 places. So they either go to RSNA or ACR, and that really, really, really rigorous de-identification and intake happens here. So these medical centers aren't working with kind of Gen 3 at large first. They're working with these professional societies, which have a tremendous amount of experience in data preparation and knowledge. And then the data goes through curation and harmonization. So this is largely overseen by investigators from the AAPM. So it was really important for MIDRC to have true kind of domain expertise in medical images. And so while software developers and different folks are certainly important for algorithm development, so too are the medical physicists and their insights and expertise in these processes. So medical physicists work on standards, annotation and labeling, LOINC mapping. So how do we take metadata and clean it up? All kinds of things. And then we have data model enabling and cohort building, and Gen 3 offers tools for this. So you can either do command line cohort building, you can build a Jupyter notebook, or you can have a totally GUI-based format of doing that on the Gen 3 data portal. But all of that is happening there. So it's very easy to build a cohort and get your patients ready to go for the next steps in your study. And when the data comes in through all of this, 80% of it goes to the open commons. So the goal is for this is to be ready to go for algorithm development, following the principles of FAIR. We want it to be trustworthy, representative, searchable, shareable, and reusable. So all of those things are happening to get that public-facing data ready. And so as of, I think yesterday, our numbers are right here. We've ingested over 300,000 imaging studies from these data contributors. About 160,000 have been released to the public, and about 150,000 are undergoing that quality and harmonization work. And the result is data that's gone through extensive work to make sure it's ready to go. I do want to emphasize, as everybody's thinking about if you submit grants to the NIH, the data sharing requirements that have changed, we are kind of eligible to help you be compliant with that. So if you want to contribute data to MIDRC, it will fit data sharing requirements, which is, I think, helpful. And you can also register it with a DOI. So this is really important for kind of saying, this is the data I worked with for this study. If you label it, if you list it with a DOI, people can very easily recreate that data set. And so we recently have a paper, I think it's about to come out any day, where we registered the data with a DOI, and hopefully can work within those principles as well. So also I want to talk about the sequestered commons. We get a lot of questions about this, but it really emphasizes that high quality nature. Training and testing leakage is a massive problem in AI medical imaging, and we need to ensure that this doesn't happen. So we have what's called the sequestered data commons, such that when the data comes in, all of the data goes through our procedures. 80% of it goes to the open, but 20% of it goes to this completely sequestered data set. And as of now, it's been building up and building up and building up, and it's not released at all. And so this acts as a large test set from which task-based samples can be drawn. So our goal is to have users come to MIDRC and say, I want to test my algorithm. It fits this profile. And here's what I want you to sample, and then we'll have kind of a containerized protected place where we test the algorithm, and then all of that happens without the leakage of the training to the test. And so we do this in a way where we anticipate users again coming to us, separating the data by some task, collecting the sequestered data set through MIDRC, and then evaluating things and getting some kind of performance evaluation. The real kind of benefit here is that this fits regulatory goals. Regulation, it's very ideal for a developer to be able to come to the FDA or other groups and say, I tested my algorithm on this sequestered test set, and it's verified by MIDRC that that process has no kind of leakage between training and testing. Hugely valuable for regulatory procedures. So that's the goal here. And so then I want to just give you a little bit of information about how that process happens. We sequester through a procedure of stratified sampling, such as this. So we start by separating by site and then modality. Right now, COVID positive or COVID negative. And the goal is to have balances between the open and the sequestered data sets. We want those to have the same profiles. And so here, we can take the data, people can use it at will for testing, or excuse me, for training. If they want to come to us for testing, they could, for example, ask us to select a data set that's set up for COVID positive versus COVID negative. We can do that to set it up. And then we can also, this process also drives our grand challenges as well. And then we can also work for COVID severity tasks. So a different number of tasks can be accomplished with the sequester commons because it is really kind of has the similar properties to the open set. And so we also work very rigorously to ensure these balanced demographic distributions. And in fact, this is a large part of my work, is making sure that as we evaluate these, they're balanced for different properties. And I'll talk more about a recent publication on that in just a moment. So in summary, these are balanced and no data leakage, and we can accomplish task-based sampling. So I've talked about the high quality setup behind MIDRC that we think is really important. And then now I'm going to talk about the representativeness of the data. And as I mentioned, one of my responsibilities is to monitor the data for representativeness. So this is a set of pie charts for the different categories of demographics that we watch within MIDRC to watch for balance. And I'll talk about what we're comparing that against in just a minute. But we're doing things like tracking by age and index, sex assigned at birth, self-reported race, self-reported ethnicity, the intersection of those, and COVID-19 or positive or negative status. And the comparisons that we do are based upon two groupings. So we're interested in, over time, how do the profiles of the MIDRC data, all of the data, compared to the US Census. So right now, most of our data contributors are based in the United States. So that's our comparison group for now, although we hope to increase that. And then we also take our COVID-19 positive patients and compare that over time to the CDC case counts. Now, you may know that in, I think, May, there was a shift in CDC reporting. So we're currently updating our comparison methods, but we're linking very closely to CDC data. I think we're going to switch to hospitalization data. And so here you can see the kind of bar charts that show up. Gray is the United States population. Blue is MIDRC, all of the patients. Red is for cumulative COVID-19 cases. And then yellow is for MIDRC. And so this is at one point in time, measuring the percentages between, for sex assigned at birth, the cumulative data in MIDRC, what are its properties, and then for the comparison groups. You'll see here JSD at the top. And so the metric that we use for this comparison is the Jensen-Shannon distance. We looked specifically to mutual information theory as a way to measure these. And we found this to be a useful metric. We're doing additional studies to measure kind of variance in this metric, its limitations, its advantages. We're pushing on that a little further, but we're using this metric for now to compare these. And so we track this over time. This is a figure that shows, I think, race over time for all unique patients in the MIDRC Open. And the Data Commons itself launched this data in August 2021. And then this is tracking through April 2023, right before the CDC comparison data changed. And so you can see some ebbs and flows in the data. And what we did was, this is race and ethnicity. We looked at the JSD kind of in 4 different formats because we want to kind of watch what happens over time. So white is the JSD, the Jensen-Shannon distance of the different kind of frequencies of appearance in the race and ethnicity category from the CDC to the census. So what we're measuring there is kind of the inherent difference in representativeness of COVID cases compared to the United States population. There were some disparities in how COVID impacted different groups. And so we would expect that to be different from the census. And so this is about a JSD of 5 here. And you can see it, actually pretty steady over this 2-year period with a little bit of a decrease. So the smaller this distance is, the closer these distributions are to each other. And then so that's kind of our baseline comparison. And then the blue is the JSD for MIDRC, all the cases to the US Census. So you can see as the data comes in, it changes a little bit, but actually, especially in the last year, it kind of has leveled out where our level of representativeness is, about 0.25 on the JSD scale. Then you can also do MIDRC COVID positive cases to the CDC. Again, a little bit of jitter as things got started with our data collection. And as you are in real time effectively comparing to the CDC case counts, but then it's leveled out here. I'll try to get that back to that slide. Good. And then the black line helps us have a quick visual about the difference in the JSD. So now we're reading from the right-hand side. The middle is 0. And this gives us a quick visual of kind of how different are those JSD comparisons to each other here. So we're continuing to monitor things, and we found this to be very helpful as we measure our intake of data. And so we recently published a paper on this in JMI, the Journal of Medical Imaging. You see here the names of a lot of midriff investigators, really great collaboration. And so that representativeness has evolved over time as the number of contributors has changed and the overall number of subjects has grown. It's leveled out pretty recently. And the use of metrics of representativeness, just as people are interested in measuring the representativeness, the fairness of algorithms, we can measure the representativeness of data too, extremely important. We want to summarize that in some simple metrics. The JSD helps that, and it's one step needed for fair and generalizable AI algorithm development. So some resources, in short, I would tell you to look at midriff.org as kind of a home base to find out more. But we have a monthly seminar series. If you enjoy those are all recorded, just like this talk is, and going up on YouTube. We have town halls, which are very interesting too, kind of a variation on presenting new updates from midriff. And we have a GitHub site where we're sharing code and lots of good things going on. And there's a newsletter that comes out too. So in summary, I hope that you found this interesting. My interests are on this patient level question of AI medical imaging. So we've been working on a measure of shortness of algorithms. We've been asking for patients where the reference standard of molecular subtype is different between two reference standards, what happens with classification performance there. And then we want to emphasize, each data is representing an individual, and that data needs to be high quality. Also needs to be representative of their characteristics that are behind the scenes in the image. And I want to take a brief moment to acknowledge several individuals and organizations, of course, midriff and the professional societies behind the scenes in there. And here are some photos of former undergraduate research students I work with. They were so great, so enthusiastic about the work, very proud of them. I'm currently working in the lab of Mary Ellen Geiger at the University of Chicago. And so here's our team there. And then, of course, grant funding is super important and super impactful for our work. So I'm grateful for the support there. And I'll pause there, maybe let you grab my contact information if you're interested, and then be very happy to discuss questions.
Super. Well, thank you very much. Very excellent talk. Lots of information there. We have time for questions. So either feel free to ask a question just by unmuting yourself and asking it, or if you want to type your question into the chat, I will read it out. And I see we already have one question in the chat, and it's actually a question I had too. So the question is, could you re-explain the sureness metric? And if I may pile on that as well, what's the difference between sureness and confidence? Because I think we're more familiar with the idea of a confidence interval, right, but it seems like you're defining something related, but not the same.
No, thanks for that question. In some ways, we want sureness to be really simple. So it has a very kind of succinct definition here at the bottom right. And then at the same time, though, it can, more explanation is always a good thing to do. So if you think about what we're doing here with this setup is we're varying the cases in training, and we're kind of with each variation in that, other cases get tested. And so, think about case A. Let's say, it's going through this evaluation process 1,000 times, let's say. It has a median likelihood of malignancy from that. And then it also, you're absolutely right, it has a 95% confidence interval of that likelihood. So, maybe that 95% confidence interval is 0.3 to 0.5. There's the 95% confidence interval there. So what we did was we really thought, though, how does this intuit with how a physician would think about this? And so our shortness metric is actually a really simple variation on that. It's 1 minus that 95% confidence interval. So if the confidence interval is very large, and in fact, we saw cases where the 95% confidence interval, if the whole scale of likelihood is 0 to 1, we saw some cases with 95% confidence interval of likelihood of malignancy from all those variations from the 632 bootstrap. That 95% confidence interval, was 0.01 to 0.99. That means that range is very broad. The model is very unsure about how that works. And so we did 1 minus that to indicate small shortness. So we're taking the 95% confidence interval of the likelihood of malignancy for an individual case as it goes through all these bootstrap iterations and doing 1 minus that. And that was driven by preparing for clinician interaction with this metric.
All right, thank you. That clears it up. Is it, again, I guess it has to do with the actual metrics you're using. Are they always normalized from 0 to 1?
We do, and I want to emphasize that as well. In our procedures, we always we use, for example, either scaling or kind of some kind of process that ensures it's going from 0 to 1, and that's kind of actually a long history in the Geiger lab, coming from this close association with clinicians. So we always scale it to that to build that intuition. Now, certainly, if you were not, you would want to construct this a little bit differently. And that would be kind of dependent upon the metric, but you can do this kind of, complement measurement that makes that shortness measurement scale to the intuition of a small value is unsure, a large value is very sure.
Right. Yeah, it would be scaled.
Mm-hmm.
Okay, that helps clear it up. We have another question here. What is the classifier used in this case? Where does the variability come from between different trainings? Is it a neural network for which parameters are randomly initialized?
Oh, great question. Neural network design and AI algorithms is so interesting and so important. And then I would also emphasize we're taking a human engineered approach here for a couple of reasons. One is I again, as a physicist, as somebody, still interested in kind of bench type experiments a little bit, if you think about it that way. I like the kind of the nature of human engineered features and how I can kind of think about them. And they also make it more tractable. A deep learning network can extract thousands of features, but then you've got to do a lot of rigorous work to filter that down. So we know that these 32 human engineered radiomic features, which are direct measurements of size, shape, morphology, we know they're useful for this task. So I would emphasize we're not using a neural network in this type of study. And then if kind of back up, the variability does come from different lesions going into training. So a 632 bootstrap is a really interesting statistical method because you can do different types of variations. You can do cross-validation, you could do separate training and tests. We've done all of those. But this one was appealing to us because the way it works is you use a given lesion will sometimes appear in training and sometimes in testing. Now, if you hear that, your alarm bell should go up. That sounds like data leakage, but there are additional statistical methods to control for that in this. So if you Google 632 bootstrap testing, you'll find some really interesting papers. And then if you're going to do the AUC from that, you need to have a correction factor. So I always like to give those warnings because you can't just flip-flop between training and testing. You've got to control for that in some statistical ways. But then that means that, again, case A, let's say its lesion appears as a test case for one iteration of the bootstrap. It's got a collection of lesions that have been used to train the classifier. Then you go through the second iteration of the bootstrap, same test lesion, but now there's kind of different lesions involved in training. So maybe some of the earlier ones were, but then there's some additional ones, and maybe some of the earlier ones are no longer. So we're varying up what lesions are being used to train the classifier. And so then that tells us, as that test lesion, whenever it appeared as a test lesion, it's had all these variations in what was used to train the classifier. We see that variability in classifier output. And this will be important, especially, AUC, always important, but also what's really important too is to think about operating points. So for example, let's say you've got a big, wide range of classifier output for a lesion. Well, then when you use one operating point, such as 95% target sensitivity, maybe it's right most of the time. But that lesion, maybe if you're using a different one, such as something that balances sensitivity and specificity, sometimes it would be right and sometimes it would be wrong. So I'd encourage everybody to make sure when you think about AUC, also think about operating points. We recently published a paper exactly on this point, providing a tool which we call performance metric curves to investigate this further behind the scenes of AUC. And so then the question about classifier, we used SVM and LEA classifiers. So I'll go to this slide here. So here, our use case was breast cancer computer-aided diagnosis, but also additionally, what can this tell us about the advantages of using one classifier versus another? This could have been any two classifiers. There's not really inherent, choices here between LDA and SVM. And what we found was if you're trying to answer that question on classifier with AUC, you've got nothing to go on. But if you think about it in terms of sureness, you can find that for a group of lesions, a lot of malignant lesions actually, for this operating point, you increase your sureness while maintaining classification performance.
Nice. Thank you. You answered that question with a sub-lecture, which is great. You actually brought up a question that I had. I think you answered it is, you talk about looking at AUC, and then I have written down, well, what about looking at the PPV and NPV? That's basically what you said about operating point is based on that sensitivity and specificity and the base rates of whatever you're looking for, what is actually the more, I guess, meaningful measure?
Absolutely. And I don't have any slides about that right now, but I would emphasize our performance metric curve paper. So if you want to jot down that phrase, we go exactly into that. We break down AUC curves into sensitivity over threshold, specificity over threshold versus threshold, and then also PPV and NPV, because we walk it through when you're using all these different operating points and you've got variability in training. How does that impact your number of false positives and false negatives at the end of the day? And so that paper walks through how to think through that.
Oh, nice. Cool. Have to look at that. Other questions for Dr. Whitney? If there's any questions in the classroom, feel free to ask them.
I have a follow-up question. What's the difference with a k-fold cross-validation for your 0.632 bootstrap?
That's a good question. So, with cross-validation, it kind of your allocations between training and testing are kind of in like fractions, like simple fractions, if you will. So if you're doing 10-fold cross-validation, you split it into tenths and then, cycle through allocations for training and testing. 632 bootstrapping really has a goal of kind of, getting more data into these allocations. And so the 632 has to do with some kind of statistical theory about if you were to randomly sample with replacement, what proportion are you likely to get? So it has behind it as well a sampling with replacement concept, which is different than cross-validation. So kind of the same ideas in some ways, selecting some for training, some for testing, and kind of cycling through. But the 632 bootstrap has in play sampling with replacement, and it controls kind of even further for those impacts on training and testing through the correction to the AUC.
Thank you.
All right, great. Other questions? We still have a few minutes left. If there's anything you're curious about that wasn't covered yet. All right, if not, with that, I'd like to thank Dr. Whitney again for presenting to us today. Thank you everyone for attending today, and have a great rest of your Friday and weekend. Thanks a lot.